In this example, we're going to consider a large cylindrical tank. So imagine that we have a large cylindrical tank with base radius r and then length L. So we have this overall length L and a base radius r. So this has has the shape of a right circular cylinder. And now this tank is laying on its side as shown in the picture, and we have a given water level. So h, little lowercase h, represents the water level in the tank. So the question is, what is the volume of water in this tank as a function of the water level? So we need to compute V of h, volume, total volume of water or liquid that we have in the tank as a function of this water depth h. So to do this problem, we first note that we can really get away with doing this as a two-dimensional problem, because essentially what we want to do is find the area against this circular end cap. So if we can find that area, we'll just have to multiply this area by L to obtain the overall volume in the tank. So basically the challenge is to find this area. So as such, let's recast this as a one-dimensional problem. So let's just look at a circle like this, and let's figure out what the area is if we have, for example, something like this. So if our water level is something like that, and then of course this bottom part shaded, what is the area of that fraction of the circle where this height is h? Of course the radius is given by r. Okay, in order to do this, first we need to identify our axis. So we need to define our variable. We need a variable of integration that's going to be integrating from this level to the bottom of the tank. So what I'm going to do for this variable of integration is I'm going to assign the x-axis like this. So x is like that. So x is going up, and x equals 0 is the center of the tank. X is equal to r is the top of the tank. And this is the negative x-axis. So x equals minus r represents the bottom of the tank. So just from experience, I'm setting this up so that x equals 0 is at the level of the center of the tank. And then x is measured from the center. So what we're going to do now is imagine our slices. So we're going to think about the Riemann sum. And our slices are essentially going to be thin little rectangles like this. So the length from the center of the circle to this slice is going to be the absolute value of x. And then meanwhile, so let's consider a right triangle like this. So we're going to use this right triangle to find the length of this slice right here as a function of x, which is basically a function of the height. So to do this, well, this ledge is length x, this ledge is length r. So the trick here is that since we have a circle, any segment going from the center of the circle to the circumference will have length r. So this is going to be length r like that. So this little segment right here will have length square root of r squared minus x squared. And notice that it doesn't care if x is positive or negative, so we can use the same formula if we're below the center or above the center of the tank. So the sign of x does not come into play for this formula. Now this only gives us half of the length that we want, because that's just this leg right here. So the total length across for this section, so basically our rectangle looks exactly like this, and then like that. So this is when we add the depth. So when we multiply it by L, we get something like this. Right, so this little piece right here going across. So the total length of our slice is going to be square root of r squared minus x squared. So that's the width across there. So basically, we just need to integrate this function over the appropriate domain, and we get the area of this portion of this circle. We get that area. Okay, so we don't go from 0 to h because that's what we would do if x was measured from the bottom and x is not being measured from the bottom. So this level here corresponds to a position r minus h, right? Because if this is h, this length will be r minus h because the overall length is r. Actually, this is negative r, so this is actually h minus r. Like this. So we always start with the smallest value. In this case, it's negative r to h minus r because we're going from smallest to the highest. This would look a little bit differently if x was going in the opposite direction. If x were going in the opposite direction, it would be, so we're starting down here and integrating. That way, if the positive x direction was downward, this would be at r minus h to r. So slightly different interpretation depending on which way. So the way I set x up was going upward, so we'll integrate from negative r to h minus r. So the total area is going to be the integral from minus r to h minus r of the square root of r squared minus x squared. You know, I think I almost like x moving down better, but let's just stick with this. Okay, so now we need to come up with an integral like this, and this, I do look like it the other way better. Okay, so that's fine. Okay, let me not set a bad example by switching definitions. I said x goes up, so that's the way we're defining x. But then again, sometimes you do need to switch because you might not have the best, you might have an insight when you approach solving the problem that you might want to go back and start from scratch and redefine your variables. But for now, let's just stick with this. Yeah, so in case you didn't see what I'm talking about, you know, positive x was going up. If positive x was going down, actually it's a simple change. Let's just do the change. If x positive is going down, so all I need to do, you can just do a little different, a different picture. Let me just redraw this. If x is going down like this, positive x, well, this is now x is equal to r, and then this level here will be at x is equal to minus r. Here's the center level, x is equal to 0. Here's the water level. The water level is a distance h. Well, then this is going to be r minus h, and this we said was r. So r minus h, I'm subtracting h from r, so this level is at r minus h. So we're integrating from r minus h to r. Always the smaller, the lesser x value to the greater. And since the integral itself just depends on x squared, it doesn't care, the integrand itself doesn't care which way we're doing this. So the area is the integral from r minus h to r of the square root of r squared minus x squared dx. So this will give the area like that. And then to get the volume of water, we just multiply it by L. So now that we have the integral set up, it becomes just a matter of integrating. Okay, for this integral, we're going to use the trigonometric substitution. So let's draw our right triangle and set it up, theta. Okay, r squared minus x squared. So that looks like r is the hypotenuse, x is the opposite, square root of r squared minus x squared is the adjacent. Now let's set up our trig relation. So sine of theta is equal to x over r. Cosine of theta is the square root of r squared minus x squared over r. And then tangent of theta is x over the square root of r squared minus x squared. From this relationship, we get x is equal to r sine theta, so therefore dx is equal to r cosine of theta d theta. So this whole integral of r squared minus x squared dx becomes, well, r squared minus x squared is equal to r cosine theta, and then dx is equal to r cosine theta d theta. So that becomes r squared cosine squared theta d theta. So basically this goes in, and then solving for, we have this also going in, r times cosine of theta. Okay, so to integrate cosine squared of theta, so this is r squared times the integral. Cosine squared theta is equal to 1 plus cosine of 2 theta over 2. We're going to do the substitution. So we get r squared over 2. We get 1/2 plus antiderivative of cosine is sine. So we get sine of 2 theta divided by the 2 on the inside over 4. I already pulled out of 1/2. Let me just not pull out of 1/2. So the integral of 1/2 was theta over 2, and then this one is sine of 2 theta over 4. So that's the antiderivative, and now we want to substitute back in. So theta is equal to the arc sine of x over r. Sine of 2 theta. That is something that seems a little bit, let's see. Oh, so there's okay, so for sine of 2 theta we can use an identity. So the identity is, so this is a very useful trig identity to know. Sine of 2 theta is equal to 2 sine of theta cosine theta. So we replace sine of 2 theta with 2 sine theta cosine theta. So this becomes r squared over 2 theta plus sine theta cosine theta. Just like that. Right, so I took out one factor of 1/2, and then we had sine of 2 theta over 2. Sine of 2 theta, the 2 comes up there and cancels out, and we're just left with sine theta cosine theta. So this becomes r squared over 2 times arc sine of x over r plus sine of theta is x over r, and cosine of theta is the square root of r squared minus x squared over r. So that becomes just over r squared like this. So this antiderivative is just r squared over 2 times quantity arc sine of x over r plus x over r squared square root of r squared minus x squared. Pretty cool antiderivative. Yeah, it looks like everything's gone. Okay, so the integral that we wanted was the integral from r minus h to r of the square root of r squared minus x squared. And that's equal to all of this stuff. And then evaluated from x equals r minus h to x is equal to r. And so essentially what we get here, it was actually 2 times this. So that cancels out this 2. Now where did I get that 2 from? We'll recall our slices. We had this triangle like this. This was r and this was x. And that one was the square root of r squared minus x squared. Well, the total length across is twice that leg. So we get 2 times this, not 1 times that. So I left off that 2 from before. So this is the antiderivative. Interesting. And let's factor in the r squared because we have an r squared in the denominator, so it's basically r squared arc sine of x over r plus x square root of r squared minus x squared evaluated from r minus h to r. So at r, we have arc sine of 1. Now the arc sine of 1 is going to be, arc sine of 1 should be pi over 2, right? Because the sine wave looks like this. So pi over 2 gives us 1. So arc sine of 1 is pi over 2. And then plus, okay, well when we plug in r here, we get 0. So plus nothing. So at the upper endpoint, we just get r squared pi over 2. And then minus r squared arc sine of r minus h over r. And then minus this one. So then minus r minus h times the square root of r squared minus r minus h squared, like that. So that is the area of a fraction of a circle. Now this one, r squared minus r squared cancels out, so then we get 2, so it simplifies as follows. So we get r squared, pi r squared over 2 minus r squared arc sine of r minus h over r, and then minus r minus h times the square root of 2h r minus h squared, like that. So that is the area as a function of the water level. And then of course the total volume, we just multiply by L, because L is this length across, so volume becomes this times L. So we can do a few things to check. So we can look at, well, what happens when H is equal to 0? You know, does this give us 0 area? Because remember, H was the water level as measured from the bottom of the tank. So when H is equal to 0, I should get 0 from this. But when H is equal to 0, well, here this term is clearly 0 because there's an H in both of them. This becomes arc sine of 1 again, which is pi over 2. So we get pi over 2 r squared minus pi over 2 r squared, so that's 0. And when H is equal to r, we should get half of the area of a circle. So when H is equal to r, we get arc sine of 0, which is 0. This is 0, so we just get pi r squared over 2. And then when H is equal to 2r, so when it's all the way filled, we should get the full area of a circle. So when H is equal to 2r times 2r. So this term is 0. R minus 2r is negative r. This is arc sine of negative 1, which is negative pi over 2. So it's pi r squared over 2 minus negative pi r squared over 2, which is just pi r squared. So that all checks out. So basically, the total area when H is 0 gives us 0. A when H is equal to R gives us pi r squared over 2. And the area when water level is 2r gives us pi r squared. So everything looks correct. So that is the fraction of the area of the circle as a function of the water level. Okay, so let's get this up top. So the final answer, the volume of water in the tank as a function of water level is pi L r squared over 2 minus L r squared arc sine of r minus h over r, and then minus quantity r minus h square root of 2hr minus h squared. Now, one thing we can do with this is plot this. So, or we can first of all do something called non-dimensionalization. So non-dimensionalization is to basically do this in terms of non-dimensional variables. So I'm going to define a new variable x, which is not the x that I used earlier. This is completely new x. So x is defined by h over 2r. So this way, the water level goes between x equals 0 and x is equal to 1. So 1 means 100% of the total length across. And then I'm going to define f of x to be, or rather just the function f to equal v over the total volume, which is pi r squared L. So this is going to be, f is going to give us the fraction of volume, so the fraction of the capacity of the tank as a function of the fraction of the height. So x basically is like a measure from 0 to 1, and then f of x will be a measure from 0 to 1. So f of x basically tells us what fraction of volume is filled in the tank as a function of the fraction of the water level. So dividing this by pi r squared L, we get 1/2 minus 1 over pi arc sine of 1 minus 2x minus, so r minus h. This last term, let's just replace h with 2r. So this last term here, we'll just do a little aside for this last term. So we'll rewrite it replacing h with 2r. So r minus 2rx. 2rx. Square root of 2h, no, h is replaced with 2rx. So 2 times 2rx times r minus h squared, which is 4r squared x squared. So we have 4r squared, looks like a common factor, so that's 2r. It's a common factor of r here, 1 minus 2x, and then square root. We already took out the 4r squared, so we have x minus x squared that we're taking out. There should be an L here. Okay, so LR squared, then when we divide it by pi r squared L, the r squared L cancel out, so it's 1 over pi, then 2 times this, so it's 2 minus 4x all over pi times the square root of x minus x squared. So if you don't believe me, you can work out the details of that. So basically all we're doing is we're taking this term up here, replacing h with 2rx, and then dividing everything by pi r squared L. So that's what we do through this whole formula. I just replaced h with 2rx and then divided everything by pi r squared L, and we get this function right here. Now this function we can actually graph, so that's why, so this, it's kind of independent of the actual dimensions of the tank. So that's why this function is nice. So any tank in the shape of the cylinder, we don't need to know what the specific radius or the height is. We can just do everything in terms of these fractions. Anyway, you can play around with this and get some numbers. So for example, if you want to find the fraction of the volume as a function of the water level, we can get some. So in fact, I actually found where the volume, you know, in percentages, so 10%, 20%, 30%, 40%, 50%, 60, 70, 80, 90, 100. Of course, 100%, the water level is all the way up. So essentially what I did is you can use a computer to invert this relation and get, well, what's the water level as a function of the volume? So in other words, you know, so here I solved for f of what value of x is equal to 0.1. And the value of x here is 0.1564755.869. So you can check that. Take this value of x, plug it into this function, and it outputs 0.1, which means that the water level, the depth, has to be 16% of the way up to get 10% of the volume. At 20% of volume, we need to be about 2541. At 30%, we need to be 0.3402. 40%, 0.4211. 50%, 50% makes sense. 60%, 0.5789. 70%, 0.6598. 80%, 0.7459. 90%, 0.8435. So basically, if you're designing a tank like this, you want to mark your water levels for the percentages. This is where you would mark them. So for example, if you're 25% height-wise, so 25% up in terms of your depth, that's 20% of the volume, and so forth. So given a given water level, this tells you how much volume's in the tank, which could be a very useful thing. And there's one simple formula that tells us, as a function of the water level, what's the volume in the tank. So if you have a tank like this and you want to keep track of how much water or liquid, or maybe it's an oil tank, something like this, how much you have left, you can use this relationship to go from the water level to just the volume contained in the tank.